since I forgot. All right. So some of you may have noticed there was some grade changes on exam 2. I might have to go back and look at exam 1 as well. There were several questions about how scores did not seem to correlate with the raw score. Turns out Canvas somehow uploaded the scores out of order. So some of you had higher scores, some of you had lower scores. So I went back to Top Hat, got the raw scores, reapplied the curve, and uploaded those scores. So exam 2 is correct. I double checked it. So those are the correct scores. And you can see the comparison between the raw score on Canvas, on Top Hat, and the one on Canvas. So the one on Canvas is the curved score. If there are any other scores that are not correlating, it looked like all the homework seemed to be fine and the exam 1 seemed to be fine. But that exam 2 was really, really messed up. And so I had to go and correct that. But that is the corrected curved score, and you can compare it to your raw score on Top Hat if you want. All right, any questions about that? Right now, we have just a few chapters left. We have chapter 12, 13, 14, 15, and 16 to get through. We've done chapter 12, and the last, the 12 through 15 are all about chemistry related to that carbonyl, this carbon-oxygen double bond. And we talked about aldehydes and ketones because they're the simplest one. Having a hydrogen on that carbonyl gives it some properties. Having 2 carbons on that carbonyl gives it other properties. And we talked about the enol ketotautomerism, and we talked about, because of the enol ketotautomerism, we get what we call alpha hydrogenation. So I'm going to go ahead and share my screen. And so it's all about the carbonyl. And so the next few chapters, we're going to be talking about additional ways on using that carbonyl. So the next thing we need to talk about when we're talking about the aldehydes and ketones is oxidation. So how do we get to an aldehyde or ketone? Well, we get to it by oxidizing an alcohol, okay? And we talked about that already in the alcohols chapter. But now let's talk specifically oxidation and reduction reactions involving aldehydes and ketones. So aldehydes can be made from primary alcohols using that special reagent PCC, pyridinium chlorochromate, okay? But what's if you already had the aldehyde and you wanted to have a carboxylic acid? Well, they are easily oxidizable either with air or with chromic acid to oxidize them all the way to the carboxylic acid. That's as far as you could oxidize things. And Courtney, yes, just email me. Okay. So the idea here is that aldehydes are fairly easily oxidizable. They can oxidize all the way down to carboxylic acids. Okay. However, ketones aren't as readily oxidizable with the chromic acid because they're stable in that form. They don't have a hydrogen that is on the carbonyl to oxidize. However, in certain conditions, specifically with nitric acid, what can happen is it'll take advantage of the enol form and it will oxidize the alkene of the enol form and turn it into 2 carboxylic acids. It's going to break the enol form and convert it to those 2 carboxylic acids. Notice this only happens at high temperatures with nitric acid. Okay. So the advantage here is that, again, it demonstrates us that the ketone form is still stable to the oxidation. However, under those acidic conditions, it can protonate and turn into the enol form, which can be attacked by nitric acid. Okay. Again, the chromic acid will not normally oxidize these, so you have to use something really, really strong. Okay. So the other way to take aldehydes and reduce them down, oxidize them down, is you can actually do single electron transfers of something. For example, in this case, we're going to take silver plus and turn it into silver 0. In the process of going from silver plus to silver 0, it's gaining electrons from that carbon, and when it does that, the oxidation state of carbon changes. So we can go from an aldehyde giving electrons to the silver, and then it reacts with water to create a carboxylic acid. But in the process, it creates silver metal, okay? And when it does this, when you do this in a test tube, it creates a mirror on the walls of the test. This is sometimes called the silver mirror test for aldehydes, okay? It's called the Tollens reagent, which is just silver nitrate and hydroxide. And then you'll get it to form this silver thing. Now, again, this is a different type of oxidation. In the chromic acid, you're oxidizing the chromium. You're using the chromium to take those electrons. In this case, we're using the silver to take the electrons. Okay. So if we can oxidize only aldehydes, and rarely do we oxidize ketones, let's go the other way. Let's do a reduction, okay? So let's go from having that carbonyl to not having that carbonyl. And we really don't break the carbon-oxygen bond during these reductions. We only break the double bond. And we can do that by taking aldehydes all the way down to primary alcohols and ketones down to secondary alcohols, okay? Because all we're gonna do is add 2 hydrogens across that carbon-oxygen double bond, and therefore it stops at that system. Now, there's a couple different ways to do that. The first way that comes to mind is, well, we did it with alkenes. Let's just use catalytic hydrogenation. Let's use hydrogen and a platinum catalyst and reduce down that double bond. And that works. You can take that double bond with a carbon and oxygen and add 2 hydrogens across it using platinum. However, it'll also reduce down any carbon-carbon double bonds. So it's not selective. It'll reduce every double bond you have and triple bond in your system by doing this catalytic reduction in with hydrogen. But the carbonyl has a partially positive side and a partially negative side. We should be able to have selectivity and only attack the carbonyl. So we have special reagents to take advantage of that partially positive carbon, that partially negative oxygen, to do very specific reductions just on that carbonyl compound, okay? And we call these metal hydride reducing agents, okay? Now, let me talk about that a little bit. So we have to have some kind of metal. In the case here, we have sodium borohydride, which is this first one right here. So it's got a sodium, it's got a boron, and it's got 4 hydrogens here. Then we have lithium aluminum hydride, okay? So I said the word hydride, okay? Hydride is a hydrogen with a negative charge, okay? So it actually has both electrons in its s orbital. It's completely filled that s orbital, and it's a very strong nucleophile because it's got that negative charge on it, okay? So now we have a negative charge on hydrogen. Why does this help us in the reduction of carbonyl compounds? Well, we have a partially positive charge on the carbonyl. And so the hydride will attack the carbon of the carbonyl and do a very specific reaction. When we have an alkene, both of those sides of the alkene are the same. There's no partially positive, partially negative side, and they don't react with them. They are very specific about reacting with only carbonyl compounds. So we have sodium borohydride and lithium aluminum hydride. Now, there's a difference in reactivity from them, and so we need to pay attention to that. Okay, in the sodium borohydride, we typically dissolve it in something like water or methanol, and what happens, it creates this complex with the alcohol or the water. And this complex is the one that actually is working to reduce down our material. We're going to have the hydride attack at the carbonyl, creating an alcohol. That alcohol then attaches itself to the boron. And then we have to clip it off with water at the end to make sure we get it to the alcohol. Note, you have 4 of those hydrides on the sodium borohydride, and each one of them can act as a nucleophile. So you can actually reduce 4 equivalents of an aldehyde or a ketone with 1 equivalent of sodium borohydride. So however many hydrides you have is how many times it can react. Okay, so the key step here is that hydride acts as a nucleophile. Okay, so let's look at that. Okay, so we have these hydrogens. It's taking both electrons with it to create the new sigma bond with the carbon here. When it does that, it kicks these electrons up, giving us a negative charge on oxygen. And then this is our counterbalancing ion. Notice that boron is attaching itself to that negative charge that's generated. And that's the first hydride transfer. And then it still has 3 more, so it can do 3 more times. Okay, but let's just say we did it 1-to-1. By adding water, we can actually break this bond, giving a hydrogen to this and an OH to the boron, and we get the next part of our product here. So the hydrogen is coming from the water, the hydrogen on the oxygen is coming from the water. The hydrogen on the carbon with the oxygen on it is coming from the hydride reagent. Okay. And again, that's the joy of having this hydrogen as a negative charge and our partially positive carbon here. We just have direct nucleophilic attack by that hydrogen. And that's why it's very selective for that carbonyl compound. Okay, so we can use this to our advantage. In that previous reaction where we had an alkene and an aldehyde, and we reduced it down with the hydrogen and palladium or platinum, it reduced down both groups. But that's not true for sodium borohydride. In the case of sodium borohydride, we can actually just reduce the carbonyl and not touch the alkene at all. The alkene is untouched, and we end up with our alcohol here. Okay. So what if we did want to reduce down the alkene and we wanted to keep the carbonyl? Okay. Well, then we have to do that trick with the acetal and protect our carbonyl from acting like a carbonyl. So in that case, if we wanted to keep the carbonyl but not the alkene, we would have to first take the carbonyl nature out of our carbonyl by turning it into this acetal, our ether. Now we can do our palladium, or in this case, rhodium on carbon, and reduce down our alkene, and then clip off our acetal to regain our carbonyl. So we finally have enough reactions that we've studied that we can start selectively picking exactly our functional groups that are on the ends. If we want to get rid of our carbonyls, we go to sodium borohydride. We want to get rid of our alkenes, we use one of those reducing agents. If we want to keep it, we need to protect our carbonyl with our acetal. Okay. So that is the last reaction in aldehydes and ketones I wanted to talk about. All right, questions about aldehydes and ketones? Okay. We learned a lot in this chapter. We learned about Grignard reagents and how they will attack to form primary, secondary, and tertiary alcohols. We learned about the chemical naming and the fact that they have the oxo if they're a substituent, or al for an aldehyde, and on for a ketone. We learned that we can rarely oxidize them. We learned that they had an equilibrium between the eno and the keto, and that would give us an opportunity to change our stereochemistry. And now we've done a selective reduction of just the carbonyl. We can choose exactly which bond we want to reduce, and we can oxidize which one we want to oxidize. So that's where we're kind of drawing this all into a close. Questions on aldehydes and ketones before I move on to carboxylic acids? Okay, let me pull up carboxylic acids then. So the next thing is carboxylic acids, and it's in this group because it has a carbonyl, but instead of having a hydrogen or a carbon on it for the aldehyde and the ketone, we now are adding other electronegative atoms. And the simplest of those is the OH group, where we've added an additional electronegative atom to that carbonyl compound. And that changes its reactivity again. So in theory, we have now 3 bonds to oxygen. So we can think of it as a very oxidized carbon. In fact, if we use a strong oxidizing agent, the product most of the time is the carboxylic acid. Okay. And we have a couple different ways of writing that, okay? This would be the way we would write it if we were trying to look at doing the resonance structure, where we have the hydrogen going back and forth between these two positions here. However, it's also COOH or C2H. That is the shorthand, but you have to remember that one of the oxygens is the carbonyl and the other is part of the OH. Okay. So we can have regular, just aliphatic ones or one on carboxylic acids. When we studied the, one on aromatic rings, when we studied benzene rings, we knew we could have benzoic acid. Okay. So naming is actually, fairly straightforward. We drop the E at the end of the word and add oic acid. So if you had hexane and you turned it into the carboxylic acid, counting the carbon with the carbonyl, it becomes hexanoic acid. Okay. However, don't forget the infix is still there. If you have an alkene or alkyne, you have to leave that infix in there. So in the case of this compound here, where we have a phenyl group, C6H5 at the end, we have our carboxylic acid, and we count 1, 2, 3 carbons. So that'd be propane with just 3 carbons, but we have the alkene. So it's propene oic acid, propenoic acid. Okay, and then we have the phenyl group on the number 3 carbon. So we have 3 phenyl propenoic acid, and it's in the trans configuration. So we have our full name here. So don't forget that infix, that's very important. And most of these carboxylic acids have common names associated with them because they're used. And this cinnamic acid actually has a cinnamon type smell to it. Okay, so let's go with nomenclature. Oh, one of the other very important things about nomenclature is if you're naming it for that carboxylic acid, the carbonyl carbon is the number 1 in your numbering system. Okay, that carbonyl carbon is number 1, it counts as number 1. Okay. In addition to that, as we found out in nomenclature and on the nomenclature review on Canvas, it takes precedent over all other groups. If you have a carboxylic acid on it, you're naming it for the carboxylic acid. Okay, so you just have to have everything else as a substituent. And what we learned in the last chapter is that when an aldehyde or a ketone is a substituent, it's called the oxo functionality. Okay, however, there are also a lot of dicarboxylic acids that are out there. There's a lot of common ones. And we would just drop the E and add dioic acid to the name to show that you have 2 carboxylic acids. Most of the time, if you don't add a number to them, that means 1 is on each end of the chain. Okay. Now, if we just name them by our UPAC naming structure, we would count all the carbons in the chain and then add dioic acid. So let's look at this one here. We have 1 carbon for this carbonyl, 1 carbon for that carbonyl. So that'd be ethane, dioic acid. Okay. We have a total of 3 carbons, so that'd be propane. So propane dioic acid. And then butane. So don't forget to count the carbonyl carbon in your main chain there. That's the important part. So then we have butane dioic acid, pentane, and hexane dioic acid. However, they also have common names. The common name for the first one here is oxalic acid. Then for the 3 is malonic acid, succinic, glutaric, and adiptic. Okay, but there's a mnemonic that you can use to remember those. Oh my, such good apple, and then the last one is pie. Oh my, such good apple pie. Oxalic, malonic, succinic, glutaric, and adiptic dicarboxylic acids. I've heard others, but that's the one I remember. And anyway, so that's how we name carboxylic acids and dicarboxylic acid. However, when it comes to a ring, of course, things change a little bit. Just like when we had a ring with an aldehyde, it was called carbaldehyde. When we have a ring and a carboxylic acid, it's the cyclo ring and then carboxylic acid. Okay, because it can't be in the chain, it can only be appendant to the chain. So we have to name the cyclic compound first and then add carboxylic acid to the end. It still takes precedent. So it's still at the end and being named for it. However, it is external to the ring. Now notice when we're numbering our ring, we again started the carbon it's named for. We don't start at the carbon of the carbonyl. That's only in rings. Don't mix that rule up with anything. And then of course we have a double bond here. So we have 2-cyclohexene carboxylic acid. And because this is opposite this is on the top of the ring and this is on the bottom of the ring, we would have them in the trans configuration. So we have 1,3-cyclopentane dicarboxylic acid trans configuration. Okay, so again, if you ever see a carboxylic acid, name it for the carboxylic acid because that's the highest priority. Okay, so once we get to benzoic acid, that is some of the simpler ones to make. It's benzoic acid. And then once you add something to it, again, it is added to it's a substituent unless you have a dicarboxylic acid. And the first dicarboxylic acid is the 1,2, and we call that phthalic acid. So let's go back to our mnemonic. Oh my, such good apple pie. P stands for the phthalic acid. It's the first dicarboxylic acid in benzene. And they have phthalic acid, and then there's the meta, and then the para right here is called tetraphthalic acid. Now that'll become important in chapter 16. We're going to talk about polymers, and this is used in a lot of polymers. So we're going to come back to this tetraphthalic acid in chapter 16. And just like before, we use numbers to denote where it is on the benzene ring. 1, 2, 1, 4, etc. Okay, so that's the IUPAC naming structure. However, sometimes we use a common naming structure. And the common naming structure, unlike IUPAC, starts at the carbon adjacent to the carbonyl. Okay, so in our IUPAC numbers, the carbonyl carbon of the carboxylic acid is always number 1. However, and it's great that we use a different nomenclature for it, when we do the common name, it starts at the next carbon over. And so the first carbon over from the carbonyl is our alpha carbon, and then our beta carbon, gamma carbon, delta carbon. Okay, so in our common names, we can tell you where the function or the other functional group is by using that denotation. So for example, this is the amino group here, and it's on the gamma carbon. So this is gamma amino 1, 2, 3, 4 butyric acid. It's the 4 acid, and oh my, such, well, those are compounds. This is butyric acid is the common name for this 5-carbon acid. This is named wrong. This is not butanoic acid. This is pentanoic acid right here. Now this is gamma amino butyric acid, or GABA. This is actually used as a sleep aid for certain types of sleeping disorders, and it can also be used as a hypnotic. So that's how we can name these using the alpha, beta, gamma. If you have alpha, beta, gamma in there, you start 1 carbon over from your carboxylic acid. So if we had that right over here, in a common name, we would call this the keto group. And so this is the alpha carbon, this is the beta carbon. So we're going to have beta keto butyric acid. But the IUPAC name is 3-oxo butonic acid. So, that is 1, 2, 3, 4. Oh no, there's 4 carbons there. I'm sorry. We switched out a methyl group. We switched out the last methylene here for the amino acid. That's what it was. I'm sorry. Okay, and so we call this actually acetoacetic acid because this little group right here, we sometimes call the acetyl group or the acetyl group. Okay, so we have the regular nomenclature, which is easy to do. We have the alpha, beta, gamma nomenclature, and we're going to hit that again in the next chapter when we're going to talk about esters. Whoa, no. There, okay, that's not exactly where we want to be, but that's all right. Okay. So, oh, I'm not going to do that. Okay. So let's talk about physical properties. Okay. So if hydrocarbons only had van der Waals forces, and that gave them very low boiling points, and the aldehydes and ketones had dipole-dipole interactions, and that pulled their boiling points up a little bit compared to their molecular weight. And then when we had alcohols, those had hydrogen bonding groups, and that even brought the boiling point up even higher. Well, the carboxylic acids can form these dimeric 8-amine ring structures and actually bond to multiple carboxylic acids at the same time. And so this hydrogen bonding brings us up to the highest amount of any group here. That's one of the reasons these carboxylic acids are the highest priority groups. They have the greatest effect on the properties because the amount of hydrogen bonding they do. They have a very acidic hydrogen. They have 2 oxygens to bond to. And so it considerably increases the boiling point and melting point of the structures. Okay. So not only are they polar compounds, but they hydrogen bond and hydrogen bond very, very strongly. So one of the other cool things that it has about it is that we can end up with something that we can dissolve in water because of the hydrogen bonding, but then it can have a non-polar tail so that it can dissolve oils. And this particular compound is called amphophilic, or it has a hydrophobic part, which wants to dissolve oils, and it has a hydrophilic part on the head. This is how soaps work or surfactants work. They have something that wants to be in the water phase with the hydrogen bonding and something that wants to be in the oil phase, and they create these things called micelles, where they create these round particles where all the fat parts are sticking in and all the hydrophilic polar groups are facing out. Okay. So let's see, hydrogen bonding rages the group, and it can have these really interesting effects with having a very long fatty tail, making it actually act as both polar and non-polar dissolving at the same time. So let's talk about them being acids, okay? Going all the way back to our acids and base chapter, acetic acid was our first and most acidic organic compound. However, it was above 0, so it's considered a weak acid. It has an equilibrium constant, and typically the pKa of these acids run in the range of 4 to 5, okay? But there are certain things that affect their acidity. Okay. So, and as we can see, when we talked about acids and bases, we talked about different effects. Now, in the case of the carboxylic acids, we have an inductive effect, how far it can pull electron density through that double bond. And so it's affected by the number of groups you have pulling that electron density. So if we just had acetic acid, we just saw that that has an acidity of around a pKa of 4.75, 4.76. And that just has hydrogens on the carbon next to the carbonyl. If we add one electron withdrawing group, one more electronegative atom, we end up pulling some of that electron density away from the carbon, which pulls some of the electron density away from the carboxylic acid, making the hydrogen more acidic. Because more of the electron density is being pulled over here, it makes the hydrogen more acidic. And we see that the pKa drops to 2.86. So that's like a whole point, right? Or 2 whole points right here. By adding a second electron withdrawing group, we see that drop again. It doesn't drop as dramatically because we can only pull so much electron density from it, one of the one chlorine and one of the second chlorine, making this even more acidic. And by the time we add our last one, we're almost a strong acid. We're almost to 0. We're pulling so much electron density out of the system that this hydrogen just wants to pop off like a strong acid. Okay. And that's that inductive effect of carboxylic acids increasing their strength with electron withdrawing groups. So it goes to say that if you have electron donating groups, it's going to increase the pKa. Okay. This inductive effect falls off pretty quickly because the number of bonds you have to pull your electrons through decreases the further and further you get away. Okay. So if we had our butanoic acid, sorry, it has a pK around that of the acetic acid, 4.8. Okay. If we put the chlorine right next to it, it'll have the highest amount of electron withdrawn. Okay. So it's going to have the greatest effect on the acidity. In fact, the acidity drops 2 whole points, and we get a pKa of 2.83, making it the most acidic of our set. If we move this chlorine over 1 atom, now it has to pull through this bond and that bond. The effect is diminished. We're only down to about 0.8 pKa value points below our starting material. So it is less acidic than its one bonded directly to the carbon next to the carbon. And if we move it out even 1 more, now it has to pull electron density through that bond, that bond, that bond, and that bond, and that bond. The effect is so diluted out, there's hardly any change in the pKa at all. So that inductive effect is by the number of electron withdrawing groups and how close you are to that carboxylic acid. So if I were to give you 2 carboxylic acids and say which of these is more acidic, you're going to look for the number and distance the electron withdrawing group is away from that carboxylic acid. All right, questions on that?
So does it only apply for halogens, or could it be any of the electron withdrawing substituents?
Any of the electron withdrawing substituents. But halogens and nitro groups are the strongest electron withdrawers. And so the effect is most prominent with halogens and nitro groups. Good question. Okay, so carboxylic acids are acidic, but if we were to deprotonate them, their new base is a conjugate base. And what's interesting is that by making it a conjugate base, they're more soluble in water. Okay, so carboxylic acids that barely dissolve in water, like benzoic acid, because of the benzene ring, you got 6 carbons you're trying to pull in with just 1 set of hydrogen bonding. By making it a salt, it actually becomes very soluble in water because it's pulled into. But we have to use a stronger base than the benzoic acid is acidic. So we have to use something strong like potassium hydroxide or sodium hydroxide. Okay. The other thing we can use is ammonia. Ammonia is a strong base, and when it reacts with the benzoic acid, it creates an ammonium salt as our counter ion and the benzoic acid salt, and these also dissolve in water because the ammonia is acting as the base, or in this case, we have the hydroxide acting as the base in our system. Okay, so this is that deprotonation, and with a strong base, it almost goes to 100% completion with our strong bases here. With weaker bases, you're going to have an equilibrium reaction. So in the case of carboxylic acid reacting with sodium bicarbonate or sodium carbonate, they do form water-soluble salts. Now, one of the things that drives this reaction to completion, even though it's a weaker base, is the fact that when we deprotonate the carboxylic acid right here and use this, take the sodium and put it on here to make our carboxylic acid salt, we create this right here. We've taken our bicarbonate solution and turned it into carbonic acid, which itself is an acid similar to the carboxylic acid. It's like a dicarboxylic acid. However, if that stayed in solution and didn't do anything else, we wouldn't be in equilibrium because this is a weak acid, this is a weak acid, we'd be in equilibrium. However, carbonic acid is not very stable and breaks out into CO2 and water. When the CO2 boils out of the solution, there's no reverse reaction. And so even when we have a weak base, which is in equilibrium, by the driving force of having the weak acid that it generates decompose, we can drive it all the way to completion even with a weak base. Okay, so we can use that to our advantage, right? If we can use a weak acid and base or a strong acid and base to deprotonate these, we can separate an alcohol from a carboxylic acid. Now, when we looked at those alcohols, we figured out that the pKa of alcohols was approximately, let's see, it's above water. Water is at 5.7. So alcohols are around 16 to 17. Right here, our carboxylic acid is right around 5, 4.75. So our carboxylic is much more acidic. So what we can do is we can take a base that can deprotonate the carboxylic acid, but hydroxide can't deprotonate the alcohol because water is at 15 and the alcohols are above that at 16, 17, 18. So that OH group will not deprotonate our alcohol, okay? Because they both have benzene rings, neither one's very soluble in water. So if we started with those two things, we accidentally had a mixture of the acid and the alcohol, we would use that acidity of the carboxylic acid to separate them. We dissolve it up in something that wasn't water. Then we'd use a base to pull that into the water layer, making the carboxylic acid only soluble in water. And when the carboxylic only acid is soluble in water, then we can separate in this case, we have ether, something that doesn't dissolve in water. And so we'll get two phases and we can separate them. And then all of the alcohol is left in that non-water phase, in this case, our ether phase. And then, so now our alcohol is completely separated from our carboxylic acid. However, our carboxylic acid is now salt, right? So if we wanted to regenerate our salt, we would have to acidify it with a stronger acid. In this case, we're using HCl. When we acidify it, it's no longer soluble in water and it precipitates out. So we're using that solubility of the basic form of our carboxylic acid to help us with separation of these two materials. So it's all about taking advantage of the acidity of our system and our solubility of our conjugate bases. All right, questions on that? Okay, so we talked about in aldehydes and ketones that we can use these hydride reagents to reduce down carbonyls, okay? So we can use sodium borohydrate and that'll reduce aldehydes and ketones down to primary and secondary alcohols. However, sodium borohydride is not strong enough to reduce a carboxylic acid. Okay, so I showed you a different reagent. The reagent was lithium aluminum hydride. Lithium aluminum hydride is strong enough to reduce down aldehydes and ketones to alcohols, but it's also strong enough to reduce down carboxylic acids. Okay, so write down lithium aluminum hydride. is the only one that's going to reduce down, the only hydride reagent we have that's going to reduce down a carboxylic acid. And because it actually reduces the carbonyl, adds a hydrogen across that bond, and it actually can reduce off this other alcohol to give us a primary alcohol. So lithium aluminum hydride will reduce down our carboxylic acid to a primary alcohol. And notice it's selective. It still doesn't touch the carbon-carbon double bond. Okay. So if you had an aldehyde, you could use either reagent, the sodium borohydride or the lithium hydride. If you have the carboxylic acid, you must use the lithium hydride. Okay. And we can use that to our advantage, again, because the carboxylic acid is so oxidized, it has those 2 oxygens on it and a total of 3 bonds to oxygen. It does not react with hydrogen and platinum or palladium. And so we can selectively reduce down our carbon-carbon double bond using that without touching our carboxylic acid. So we don't have to use the trick we used in the aldehyde or the ketone, turning it into an acetal to selectively reduce down. It is not reducible under these conditions, and we can just get rid of the carbon-carbon double bond. Okay. So the other thing about selectivity is that the sodium borohydride doesn't reduce down the carboxylic acid, but it does reduce down aldehydes and ketones, which means if you selectively wanted to take a ketone and turn it into the alcohol while keeping your carboxylic acid, you wouldn't use lithium aluminum hydride. That would reduce down both of them. You would use the sodium borohydride. It will only reduce down our aldehyde or ketone, leaving the carboxylic acid alone. So now when we think about our reagents, we now have selectivity, and we can choose our product based on the reagents we choose. So knowing that which reagent reacts with risk groups is going to be important as you go through your homework and our next exercises. Questions on that? Okay. Let's see. Okay, so here's another reaction that can happen. We call it the Fischer esterification, and it's an equilibrium reaction. Okay, so the idea here is that you can take the carboxylic acid and react it with an alcohol in the presence of an acid catalyst. And what it's going to do is it's going to remove water and create a new bond called an ester. Okay, we're going to talk about this a little more in the next chapter here, but the carbonyl OH, and R can be any alkyl group, we take that H off and we add another bond to an R. Okay, so that's what we've done. We've gone from that carboxylic acid and this carbonyl OR bond here is our new functional group called an ester. Okay, and we can make the reaction go either way depending on how much acid or how much water, how much alcohol and how much water we have on either side of the reaction. Okay, now it's hard to get 100% all the way one way or the other way unless you're using something with a very big difference in use like 100 times of this and that. You can drive it to completion. Okay, so I said it's an equilibrium reaction. It's acid catalyzed. All right. So the first thing we do is we have to have attack by a nucleophile somewhere. So in this case here, we're using the alcohol, the lone pair on our alcohol as our nucleophile to kick this open, and the acid protonates the OH group. This is the key step here. We go from that sp2 hybridized carbon to an sp3 hybridized carbon, but notice it has 3 oxygens around it. Okay, so that is not really stable, and what's going to happen is that one of the hydrogens and one of the OHs is going to leave, regenerating our carbonyl compound. So that's the driving force, is to reform that carbonyl compound, which is more stable, and get rid of a small neutral molecule. So in the case of acid catalyzed, we're probably going to be protonating the carbonyl here, making it a much better, much more electropositive here, allowing us to do the attack with our nucleophile. Okay. All right, so with the carboxylic acid, we took a carbonyl and added a more electronegative atom with oxygen. And in the case of having a hydrogen attached to the oxygen, it was the carboxylic acid. Okay. And in the case of the ester, we still have a more electronegative oxygen to it, but we've taken off the hydrogen and made it into a carbon bond there. So we still have a more electronegative atom attached to a carbonyl. Okay. So another electronegative atom we can have is what we call acid halides, or basically acid chlorides. We can take that group, that OH off, and put an even more electronegative group, in this case a chlorine on it, and that actually makes it really, really reactive. We call these acid halides, or most of the time we use chloride because the others are a little too reactive. And so we have what we call acid chlorides. And in the case of this, we'll name these, I think, in the next chapter as well. This is the acetic acid. We converted it to the chloride, so it's acetyl chloride. This was benzoic acid, and so we've converted it to the chloride, so it's benzoyl chloride. What's the advantage of going from that oxygen to the chlorine? Okay. The advantage is the reactivity increases. Okay. So we have a more polar bond, we have greater reactivity at that site. Okay. But it's kind of hard to prepare them because you don't want to just have OH as a leaving group for the system. So what we do is we prepare them with a compound that we used in the alkyl halides chapter to do primary alcohols. And it's thionyl chloride, SOCl2. Right here. And what we're going to do is we're going to do that same trick we did with the alcohol, in the fact that we're going to form some kind of sulfur oxygen bond here first. And then we're going to have that leave as a group and having our chloride attack as our nucleophile to give us our acid chloride. And then this goes off as a gas, this goes off as a gas, and it drives the reaction to completion. Okay, so this is how we, most common way to prepare acid chlorides from carboxylic acids. Okay. So let's see, what else can we do? Okay, we've replaced with more electronegative atoms to make them more reactive. But the other thing we can do is we can lose CO2. We already have a carbon bonded to 2 oxygens and it has 3 bonds to it. CO2 just has 4 bonds to oxygen. So we can do that. Now, it's not very easy to do without certain conditions being met. So if you were just to take any old carboxylic acid and heat it, you'd have to heat it to 300-400 degrees to get it to lose CO2 and form a unfunctionalized hydrocarbon. However, if we take advantage of that, the electron withdrawing of our carbonyl compound here, we can actually make it easy to do this decarbonylation. And what we call this is a beta keto acid will undergo these eliminations very readily. So what does that look like? Okay, the whole key here is that we have a carbonyl compound that is one spacer over from the carboxylic acid. Okay. Now, how do you remember this? Well, the way to remember this is that it's going to be forming a 6-membered ring in its transition state. Okay. So the key here is that we are going to redraw our carboxylic acid such that the hydrogen is adjacent to our carbonyl of on the beta carbon. Okay. This makes it much more easy to see how the elimination happens. In this case here, it undergoes a concerted reaction, meaning it happens all at once, where the electrons from the carbonyl of the ketone flip up. The electrons that were on the hydrogen to the oxygen kick down. Notice that's going to give us a double bond here. And then the electrons that were on this carbonyl kick over here, and that's going to give us our enol form and CO2. And then our enol form will rearrange to be our keto form, and our CO2 goes off as a gas. So because of this transition state, the direct transfer of the hydrogen to that carbonyl, it makes it very easy to do this thermal decomposition. Some of these can happen at like 50 or 60 degrees because of that transition state. Okay. So let's see, the reactions of carboxylic acids we have are react with base. We can reduce them down with lithium aluminum hydride. We can make them into esters. We can make them into acid chlorides. And we can shorten the chain by 1 carbon by decarbonylating it. Okay, notice we've lost 1 carbon in our chain, and we've changed our functional group during that decarbonylation reaction. Okay. That's the, oh, okay. But it doesn't have to be just a ketone. It can be any carbonyl compound, okay? So in this case here, we're taking a dicarboxylic acid, the malonic acid, and we're doing the same thing. All we have to do is have that ketone, that carbonyl available to us to form that 6-membered ring transition state. Then we flip our electrons here, and then here, and then here, giving us our enol form of our carboxylic acid and CO2. And then this hydrogen gets transferred back to give us our full carboxylic acid. Notice we still lose a carbon, but we had 2 carboxylic acids to begin with, and we ended up with 1 carboxylic acid at the end. Okay, so as long as that other carbonyl is in that beta position, you can undergo these thermal decompositions to remove 1 carbon with CO2 and end up with your other carbonyl compound. In this case, the acid. Questions on thermal decarbonylation? Okay. Okay, so let's put it into practice, okay? So when we think about this, we need to make sure that our carbonyl compound is on a beta position. And then we need to figure out which carbon's going to leave. Okay, so let's look at this first one right here. And if we do this, I want to redraw this such that our O is up here and our H is over here and our carbonyl is here. So I'm going to hide that right there. That's going to be gone. When I redraw that such that that forms that 6-membered ring, it makes it easier to see where the electrons are going to go, right? Because the electrons are going to come here, the electrons are going to come here, and these electrons are going to come here. That means we're breaking this bond when we do it. And when we, so our enol form is going to look like this, plus CO2. See, we're forming a second bond here, and we already have the 2 bonds there. And then, of course, it'll switch back to its keto form, which is the more stable form, right here. So by keeping track of which bond breaks, we can actually make sure that we draw the correct final product. So let's look at this problem and say, what did we start with? Okay, so let's figure out which carbon the carboxylic acid had to be on to give this product. Okay, so let's see, we have our ketone here. All right, we have our ketone here. And so our carboxylic acid had to be in a beta position to it. So, well, okay, that is the alpha position, beta position. This is alpha position, beta position. So we have to figure out where that is going to attach to. Well, we can't use the benzene ring because it's actually has too much energy aromatizing it. So we have to do something on the other side. All right, so it can't be there. So we need to find out that it's in the beta position, okay? But that means the carbonyl has to be attached to an alpha carbon to have the other carbonyl be on the beta carbon. So we need to find a carbon that's adjacent to the carbonyl and attach our carbonyl to it, our carboxylic acid to it. So we have to put our carboxylic acid right here to be able to, oxygen, to be able to form that six-membered ring, because now we have, let me redraw that. We needed to have it where we could OH, draw our six-membered ring here to create our thing. So we had to find this carbon is actually our alpha carbon, and that's the one we had to put our carboxylic acid on to find our starting material for this product. So the forward reaction is losing that carboxylic acid off of that beta carbon and leaving the carbonyl on the beta carbon. In the back reaction, we have to attach a carboxylic acid to that alpha carbon, and knowing that this becomes our beta carbon when we attach our carboxylic acid to it. So that's the key to picking out your products and starting materials in the thermal decarbonylation of carboxylic acids, specifically ones with beta carbonyls on. Okay, and so that is all I have on carboxylic acids. We have 20 minutes left, so let me go ahead and download my slides for carboxylic acid derivatives real quick and ship them to myself. I thought I'd done this, but apparently not. Okay. Past semesters. Those are really PowerPoints. Where are the slides? I'll just cancel. I'll just download them from Canvas. Slides, videos. Okay. We're looking at chapter 14, carboxylic acid derivatives. Or how big this file is. There it is. Not bad at all. All right. I'm going to download it right now and we can get on. Okay, let me share my screen again. All right, functional derivatives of carboxylic acids. All right, so we have carboxylic acids themselves, and they have a few reactions they do. But one of the more powerful things that these carboxylic acids do are that we can derivatize them. And when we looked at IR, we could actually follow that carbonyl around as it changes from an amide to an ester to a carboxylic acid. We can see that change in IR. And so let's go ahead and look at some of these functional derivatives and define them by class, okay? One of the things that you can always look at is, okay, all of the carboxylic acid derivatives are basically reacting something with something and removing water, okay? So they can all be kind of described as this. It's not necessarily how we make them, but it's how they can be described. So the most reactive of the set is what we call the acid chloride. We talked about that before in the last chapter. However, if we think about using the carboxylic acid and using a strong acid like HCl, and we remove this water portion in the middle, creating the bond from here to here, that's creating our acid chloride. Okay, so it's a metaphorical removing of water. We don't actually make it this way. Okay. However, in making it the anhydride, this is actually how we make it. We remove water from the system, and we notice we have two carboxylic acids, and we've removed one equivalent of water between them. And that gives us what we call our acid anhydride. Okay, so it's our acid anhydride because we removed water. So all we have is two carboxylic acids and removing of water. Now, we talked about this already. We have an ester. We have a carboxylic acid and an alcohol. And if we remove water from that system, we end up with that ester. And the last set is when we have an amide. We have a carbon-nitrogen bond here. Again, we're taking the hydrogen from the nitrogen and the OH from the carboxylic acid to generate this new functional group, the amide. So it's a carbonyl nitrogen is an amide, carbonyl oxygen carbon is an ester, carbonyl oxygen carbonyl anhydride, and carbonyl chloride acid chloride. Okay. So the cool thing about these derivatives is we're changing the reactivity of this carboxylic acid by changing to these different derivatives, okay? So let's start naming these things. When we name acid chlorides, we had oic acid as our name at the end. What we're gonna do is we're gonna drop the IC, so we're gonna keep the O. We're gonna drop the IC and add YL. So it's gonna be ethanoyl chloride, okay? So again, we're leaving the O from the oic acid and we're adding a YL. So it's ethanoyl chloride. Or if this was benzoic acid, it's benzoyl chloride. Okay. So that's how we would name that group. And it's having everything to do with the idea that it was the carboxylic acid, this part here, but we swapped out that OH for that chloride. And so that's how to name that. Okay. All the other rules apply, and the carboxylic acid derivative is going to be what it's named for. In the anhydride, we have a couple different ways to do it. Okay. If we have the same group on both sides, in like here we have acetic acid and acetic acid, we can just say what the carboxylic acid was and add the word anhydride at the end. Okay. If they're mixed, you have to say what the two different carboxylic acids were and put them in alphabetical order. Okay. And we just take the acid name off and add the word anhydride. So in this case here, we have acetic acid, we have benzoic acid, but it's an anhydride. So it's acetic, benzoic, anhydride. Okay. Now this is one of the weird ones. This is a dicarboxylic acid with a double bond on it. We call that maleic acid. Okay. All right. Okay. And this will become much more important if you go to the follow-on biochem course here. These phosphoric anhydrides are used extensively in the biological systems. And this is basically the same kind of system where you are creating an acid and an acid, and you are removing water to create a multi-acid system. So if we remove one equivalent of water with two phosphoric acids, we have the diphosphoric acid, sometimes called pyrophosphoric acid. And you can also make the salt out of this, and it's called the diphosphate ion. Now, you may have also think of, well, we can do it again to make this triphosphoric acid, and that makes what we call the triphosphate ion. And so what you'll see it done in lab is it'll be like the tris phosphate buffer. Tris phosphate buffer is a salt of the triphosphate ion. Okay, now these are very extensively used in biological systems. In fact, it ionizes at the pH of blood and is used in our DNA and other things. Okay, so that's the anhydrides. The esters are a little bit different to name because what you're going to do is you're going to name it for the carboxylic acid, but then you also have to keep track of the alcohol it's made of. Okay, now it's no longer an acid, so we're going to drop the ic acid. Again, we're keeping the O, and we're adding the word ate. Ate describes something that's a salt or an ester. Okay, so in this case, we have right here, this part right here is ethanoic acid. Okay, so we have ethanoate is our ester portion, but we have to name the substituent. So this is the 1,2 carbon, so that's the ethyl group. So that's the substituent on our ester. So we have it ethyl ethanoate. If we wanted to name it by its common name, we would say, oh, that's acetic acid. So we have our ethyl group, and so we have ethyl acetate. Okay. So if we have something more like this, we have a dioic acid here. So we're starting with a dioic acid here, and it's 1, 2, 3, 4. So that's butane dioic acid, but it's no longer an acid, it's an ester. So we drop the ic acid, add O8. So butane dioate, okay? But we have to remember the attachments, and we have ethyl group here and an ethyl group here. So we have diethyl butane dioate. Okay, but this also had a special name. This is succinic acid. Oh my such. So succinic acid and diethyl succinate. Okay, and that works with any group bonded to it, an alkyl or an alkyl group. Okay, and it's usually, well, I'll get to that. Okay, now we're bringing back the alpha, beta, gamma. Okay, if you end up having an alcohol on one end of your chain and a carboxylic acid on your other end of the chain, and you lose water to make a cyclic ester, notice the ester is actually in the cycle right here. Okay, we call these lactones. Okay, and so it looks like a ketone, but then it has this extra oxygen on it, so we call it a lactone. We're going to drop the ic acid off of it and add the word lactone, keeping the O again. So butanolactone. Okay, but if we have it with the IUPAC, we use numbers, and we're going to start with the carboxylic acid as number 1, and we're going to go all the way up to 4, and that's where the oxygen's attached. So we call that 4-butanolactone. Okay. But if we use the common name, we have alpha, beta, gamma. So this is just gamma lactone. Okay, so it's simpler to name it with that system. So, and when we have cyclic amides, we're going to do a similar naming with the alpha, beta, gamma system. For our phosphate esters again are used extensively in biological systems, and you'll learn a lot more about this if you do the follow-on course. I don't do very much with the phosphate esters. But the next functional group I want to talk about, though, is the amides. Okay, the amides is we're replacing that OH from the carboxylic acid with a nitrogen. Okay, but just like amines, it's all about how many carbons are bonded to the nitrogen. So when we have an amide, the first carbon bond to the nitrogen is always the carbonyl from the carboxylic acid. Okay, and if we only have that carboxylic acid bonded to it, we call that a primary amide because it has one carbon bond to the nitrogen. If we were to take off one of those hydrogens and turn it into a different functional group, we would have to call that now a secondary amide because we have two carbons bonded to it. And if we did it again, we'd have a tertiary amide. Again, the amines are weird. It's all about how many carbons are bonded to that nitrogen. Okay, but when we do those substitutions, just like the ester, where we have to make sure we know what that substituent is, we have to show that it's on the nitrogen. So in the case of this system here, we added a methyl group. So just like we'd have methyl acetate, where the methyl group is the attached part of the functional group, we have to say the methyl group is attached to the nitrogen with this N right here. So that N-methyl is talking about the substituent. The acetamide is talking about the amide here. Okay. So, oh, I forgot to say, you drop the ic acid and add the word amide. Okay. Actually, it's oic acid. So acid amide in this case, or butamide. And then we add, and if you have two of these on there, you got to show two of them on there, N, N, dimethyl form amide. This is formic acid. It's one of the simplest carboxylic acids we have. And so it's dimethyl form amide. Okay, so we have to have three, okay, yeah, you have to have three things attached to nitrogen. So it can be two hydrogens, one hydrogen, or no hydrogens at all. And there, all right. So just like we could name the cyclic ester differently, we named cyclic amides lactams. Instead of lactones for the carboxylic acid esters, we name them lactams, okay? And we do what we've done with the other ones, drop the ic acid and add the word lactam. So it's butanolactam, hexanolactam, okay? But when using the alpha, beta, gamma system, it's where it's attached to the nitrogen, okay? So in the case of this one right here, it's beta-lactam because that's it's not the end of the chain, it's where the nitrogen is attached. In this one, it's an epsilon lactam because it's where the nitrogen is attached. Alpha, beta, gamma, delta, epsilon in order. Okay, so the carboxylic acid derivatives have this really easy stepwise name. Carboxylic acid is the parent, change the name to the functional group. Carboxylic acid is the parent, change the name to the functional group. And so let's talk about some practical uses for these functional groups. One of the penicillin, name of the penicillin family is amoxicillin. It tends to have fewer side effects than penicillin on some people. And it actually has a couple different functional groups available to it. It has a carboxylic acid in it, so that's interesting. It's got an amide in it, and then it has a lactam in it. So if we look at our system here, we have our carboxylic acid as part of the functional group. We have our amide as a second part of our group here. And we have the third part of our group here is a amide, the lactam, the cyclic amide in this ring. Okay. This is true for other derivatives here. Notice it's changed slightly. We have a bigger ring here. We don't have the 5-membered ring. We have a 6-membered ring, but it has some of the same features of the lactam, the amide, and the carboxylic acid. And we've changed the functional group here. So we can use these different functional groups in a lot of our everyday biological system life. Okay, I'm going to stop there, and we're going to continue on with the characterization of the different types of reactions we have on, on Thursday. We'll do that on Thursday. Okay, so I'm going to stop recording. Stay behind if you want to ask questions, and leave if you have to go.